Okay. I'm pretty sure we're recording. If we're not, then we're not. All right. Okay. Cool. So we're done with a lot of the tooling you guys need to know. So you're experts at testing, compiling, running stuff on Whistle. All the infrastructure should be set and working well. Um, expert, pro level. How's the programming assignment coming along? Slower, getting there. Slower, yes. All done.
You're going to show stuff with the serial library?
No.
Okay. Because I was trying to find documentation for it,
Uh-huh.
for the deserialization, and wasn't really gaining a lot of ground. I don't know. Couldn't find a good, like, applicable example, I guess.
Okay.
But
How are other people doing with serial?
I know that Stacy gave me a good direction.
Okay.
I feel like writing is easy, but I've had some trouble getting it out. But after talking to, I think
Okay.
I'll talk to this again.
Yeah. Great. So, from my perspective, the way I like to do this and other courses, and so this course is let you guys kind of explore stuff on your own a fair amount, right? Now, this requires a fair amount of banging your head against the wall, and I see my job as limiting that to the right amount. Because if you don't do that, then you don't get to learn, you don't get to develop like a tough skin and sort of a sense of this indignant feeling about not being able to figure something out, even given shitty and out-of-date documentation, right? When I talk to my grad students, I explain to them that the key to success is the ability to demonstrate getting consistently lucky. Right? And that's how I think of system. That's how it is, right? So if you can consistently get lucky and find the right documentation, find the right option that wasn't documented, or find some ways of combining two things that miraculously works, right? That's kind of how a lot of stuff gets implemented. And then as you get better and better at it, you develop like a sixth sense of what's going to work, what's not going to work, or what pieces are missing, or where to find it, or how to ask a question, right? And that's something that I can't really teach you other than creating an environment where you guys try, right? So if the documentation is bad, that's actually not a bad thing for you. Now, if you are getting stuck, then eventually you do need to ask for help or talk to other people or talk to Cooper or talk to me, right? So I fully appreciate how frustrating this process is, and I can assure you it does not get easier. This is a piece of advice that I got from my advisor, Kevin, in my PhD program, where I was like overwhelmed with papers and trying to get results and nothing was working, and and then papers get rejected, and I feel like I'm working all the time. And I talked to Kevin, and I'm like, Kevin, does this ever get easier? And he's like, no, it gets harder. And I'm like, what are you kidding? He's like, no. And it's true. And I don't know, it sucks, it's great. However you want to look at it, it's just how it is. So anyway, back to your point, I'm creating an environment where you guys get a test for it. If it gets too hard, or if you really need help, or if you feel something is consistent, seek help, talk to other people. Talk to me, I always want to hear what's going wrong, because if the barrier is too high and you guys can't grab the ledge, like I need to fix that for you or for other classes. All right, maybe that's too much of an explanation, but just so you kind of know what I'm trying to do here with you guys. Okay, so Any other comments on the programming assignment? No? Okay, cool. All right, so we move into computer architecture eventually, I think next week, starting into assembly, which will lead us into the second part of your project where you'll be optimizing storage of the game data. Instead of using JSON files, you'll be using assembly to do that. Okay. Okay. So which of these would you consider a computer, and why? All of them? Yeah? Takes input and provides output. That's your criteria. Okay. Stores data. Okay.
argue the car uses computers but isn't a computer
Why not?
because it's largely mechanical and there's a lot of computer systems that control all the mechanical.
So there's like microcontrollers.
It's just a crap ton of microcontrollers.
Yeah.
Computers everywhere in it, but it's not on the whole.
So what's the difference between a microcontroller and a computer? Hmm.
Is it an operating system? Like a microcontroller you can just flash, whereas a microprocessor or a computer is an operating system.
The operating system is one way of running stuff, but it's not the only way. You could run, I mean, an operating system is itself a program. It just has little special privileges.
Desktop computer, like a laptop and a microcontroller.
Hmm.
Microcontrollers, whatever they're designed for, that's all they're meant to do.
Ah.
And whereas a desktop computer or a laptop, it's designed to be modular and you can program, you can do the internet, you can do whatever you need.
The term you're looking for is general purpose, right? It could be used for many different purposes, whereas a microcontroller like controls ABS on your car. That's it, right? It's not going to mine Bitcoin.
But that's not to say it's not a computer, because it's totally a computer. In my opinion, microcontroller.
So, of course, debatable. We'll refer to computers as computing devices that are general purpose. Could be reprogrammed to do different things. Now, microcontrollers are getting powerful enough that you can reprogram them or reflash them, right? So the boundary can be somewhat hazy, but the general purpose is the thing we're looking for, right? So obviously, that's a general purpose thing. That's a general purpose thing you can build, which looks a lot like this, except it's smaller. Okay. Tesla car. Tricky, right? Is it general purpose? Not really. It just kind of drives the car. But then the console in it can do all kinds of stuff. In fact, Teslas have a powerful enough computer that they can be programmed to mine Bitcoin quite efficiently, which someone has done. There's actually a super beefy computer inside those things. So, so general purpose made not general purpose kind of thing. All right, a calculator. This type of calculator cannot be reprogrammed, right? So if you think of like a TI-83 or whatever graphing calculator you guys are using now in calculus, right? Those can be reprogrammed, but something like this really cannot. It's all just hardware, right? And this is what a computer used to be. A computer used to be a person that did calculations before we had machines to do that. So that's where the term computer comes from. All right. So if we abstract a general purpose computer, you'll see that they really have a very small number of functional units that do different things. Okay? So what computers can fundamentally do is produce output and take input. So you have some sort of an I/O module. And this could be anything from your display to keyboard to mouse to printer, anything that kind of moves data in and out of the computer, which can also include the network. You can also think of a network card as an I/O device, especially the way it's connected to the rest of the computer or to the other components. All right, so generally moving data in and out would be in the I/O. Okay? Then you have storage devices, which store your data, your programs, everything. Okay? And they can they exist in a hierarchy of things. So you can have random access memory, you can have disk, you can have whatever else you want that just stores data. And then you have a processor, which is generally divided into two things. One is the arithmetic and logic unit, and the other thing is the control unit. Right? So the ALU does the actual calculations like addition or subtraction or division or the OR operations, the AND operations, all the kind of things that manipulate bits. And the control unit is the thing that moves your program along. Right? So often these are kind of tied together on a chip. So this thing would be called the CPU. Okay? So I want you guys to give this a try. Let's find groups of 4 people. Each person, oh my God, each person can pick a role of one of these things and try to coordinate together to compute the mean of these numbers. Give it a try. Okay. Great. Sweet. Awesome. I'll see if I can enable this for you. What is the announcement about? Should I make it in class?
Start the project, look at IO stream,
Yes, before they ask you. Right. Okay. Okay, I'll say something. If I don't, just raise your hand. I'll remember.
You got a rebellion in the ALU. 27, the mean at 27. Did I calculate that right? All right.
Well, okay, I'll do arithmetic.
All right, I'm putting 13.5.
13.5? Okay.
As fast as you can.
Well, like it's mental math, and all that's of the 25.
I'm data storage.
That sounds like, that seems really wrong. How is that higher than every number?
All right. So what approaches are you guys taking? How did you assign the work? All right. So let's talk about I/O. Who are the I/O units? Okay. All right. What is your process?
I read the numbers off the board to our data storage.
Okay. You read it to the data storage. What'd you guys do? Yeah. But the I/O does not communicate with the data storage.
Good point. The controller told me to.
The controller told you to. But the controller told you to read in the data, but then where did you send the data? Anyone send the data to the controller? Yes, nice. Okay. All right. So then who are the controllers? All right. What did you guys do with the data that you got?
I sent it in to get processed by our friend here at ALU.
All of it?
All of it.
Okay. Anyone did something else? All right. So here's the thing. I/O can only talk to the controller. Now, the controller doesn't have all the memory, right? So if I give you a list of 1,000 numbers, the controller can't keep all of that. They need to go to data storage, right? And the ALU can't hold all that data. The ALU, how many numbers can you add simultaneously?
At least one.
2, probably, right? Adding 3 numbers at once, I mean, maybe you can do it. We're really not used to doing that, right? But you'd probably do is add the first 2 and then add the third one. So you're only adding 2 numbers at a time. All right, back to the drawing board. Figure out the rest of the process.
So first input is 5.
First input is 5. First input is 5. Second input.
Second input is 9.
Second input is 9. Second input is 9. Or I guess input is 9.
Oh, now, okay. Return of 14. Or 14. Sum is 14.
Store 14. What's the third?
Third input is 7.
Third input is 7. Third input is 7. 21. 21. Score.
Okay, all right, but what are you doing? You're doing addition? Is that your default operation? Is that the only operation you can do? Then how do you know to do addition? Ah, controller.
It's all my fault.
What is? It's everybody's fault. You guys all have distinct functions. Everything has to work.
All right.
All right, how are you guys doing? Yeah? All right, let's bring it in again. So now we're doing this one number at a time. We're reading in a number from here. Okay, controller takes that, puts it in data storage, then transmits it to the ALU. And then the controller also has to tell the ALU what operation to do. Right? You can't just give the ALU a number and hope for the best. You have to tell it to do an addition.
It was doing pretty well on it.
It's doing pretty well. Okay, as you're doing addition, right? Saying, oh, here's the next number, here's the next number. You need to compute the average or the mean. So you also need to keep track of how many numbers you're adding together to do the division later, right? So there's this notion of an algorithm, right, that the controller has to execute, right? And the ALU can only do different things, right? Just like a calculator only has some number of functions, right? You got your plus, you got your divide, right? You got a tell. Like when using a calculator, you're basically executing some algorithm as a controller, punching in the operations. Okay, so that becomes your assembly code or your machine code. You're basically telling the ALU to do an addition, and then you give it 2 numbers, right? But then you also need to keep track of where you are in the algorithm, and that has to be somewhere. Now, I told you guys to compute a mean, and basically all of you are turning into, all the controllers are turning into a purpose-built machine that somehow knows how to compute averages, right? But if you want to be general purpose, then you need to execute a program. Where is that program stored? Presumably in storage. So how does the controller know what the next step is? Program counter, right? So there's some pointer that kind of says, here's the next instruction. But then before the controller says, hey, ALU, add these 2 numbers, the controller needs to know that it's doing addition, which means it needs to get the next instruction from data storage. Okay, this whole process is cumbersome, right? But it can be implemented step by step, and there's no magic to this, right? You have very simple actions, which is like, okay, get the next instruction. Okay, it's addition. All right, let me get the numbers. Okay, it's these 2 numbers. Okay, now I can pass this to the ALU. I get the result. Okay, I write that to memory, figure out the next instruction, do the thing, right? It's very, very simple. It's like using a calculator. You have some sequence of instructions. You punch them in one by one, and the state changes, and then you get a number. Yeah.
So it kind of feels like the chicken or the egg problem. It's like the controller needs to know that it needs to run a program in step, but then it needs something to tell it to like run the program. And like, where's the initial like, go?
Where's the spark?
Yeah.
It's a good question. We'll come back to it. All right. So, questions? Anybody else? No? All right, let's move on. So, you can look inside a computer, and you can look inside a computer, and you see that they're all really the same things, right? Inside a laptop, you have your processor, which sits here. You have your hard drive, which sits here. You have your slots for memory. You have your I/O, right? And then if you looked at a computer from like 1960s, you would see the same things, except you are now inside the computer. It's like the Matrix, right? Where you have, I don't know, you have your output here. It's on a printer. You have some console. You have main processing and main storage. You got some other I/O, right? It's just all distributed throughout the room instead of being inside a laptop enclosure, right? But it really corresponds to this model that we've been talking about. And then you can descend into an actual chip, and you'll see the same exact architecture, right? So here's a chip with 4 cores, and you can look at that kind of on this diagram, and you see you have cores 1, 2, 3, 4. And then inside a core, you have different caches. You have your control units. You have your ALU here. It's all basically the same thing at a smaller scale. Right, so it gets smaller and smaller and smaller, or larger and larger and larger, but the functional units remain the same. All right, so where does this idea come from? How did we get to this organization? Right, there seems to be something fundamental about how computation is performed. Okay, so if we go back to 1940s, we started having first computers. Now, initially, the first things that did computation electromechanically were things like the bomb developed in England to crack Enigma. But it was purpose-built. That thing only did one thing, which is crack Enigma. Okay? The first general-purpose computer was developed at my alma mater, University of Pennsylvania. And what made it general-purpose is it was supposed to be a machine to do calculations, but it was designed for ballistic trajectory calculations. Basically, when you build a new artillery piece, you need to know how it would fly under different conditions, how it would shoot, right? And as the war was nearing the end, the army didn't need it to do those types of calculations as much as it needed it to do calculations on hydrogen bomb design. So you had a computer that was developed for one thing and then reprogrammed to do something different. First general-purpose computing machine. Pretty cool. Now the question was how to program this thing, right? And a lot of programming was done actually by women. So men kind of designed the hardware, but they had women mathematicians do the programming. And what they discovered is that if you took one of these cables and bent it just the right way, you could create a conditional statement. And once you have conditional statements, now you can do general purpose programming. Right? So that's how this started. Like, be thankful your job is not trying to run Battleship by bending cables just the right way. All right, so, but this thing really just did computation. You had to enter data on these dials to dial to the right number, then connect these things through a cable to the thing, you know, just awful. All right, so then from there, von Neumann invented a generalization of this by developing the stored program concept. Back here, you had kind of your program, which was how you connected these different wires, and you had your data, which was entered into using these dials. Right? So separate programming, separate data. Yeah.
Do you have any idea how bending wires would create a conditional statement?
Has to do, I don't remember, it has to do with like voltage, where you change the resistance and that somehow did the thing. I don't know. Electricity is magic. If you're interested, there's great history books on the ENIAC. Okay, so you had separate programming, which was here, and separate data, which was here. And so von Neumann realized that it's all data, and you can put it all inside memory. Okay, so you can have memory that stores a number, right, with one bit for sign, positive or negative, and the rest of the bits used to encode a binary number. And then you could store a program also inside the same, also inside data, where you have some operational code and then a memory address. Okay, so the memory address would refer to some address storing the data, and the opcode or operation code would refer to the operation you're doing, which is pressing a plus button or pressing a minus button on your calculator. It's just an operation. Okay? So by going through a series of operations, you could transform this data. Stored program. Super revolutionary. Okay? And he built a machine, and he also came up with this idea of separation. So you had your main memory, you had your I/O, you had your program control unit, and you had your arithmetic and logic unit. Right? And that's the von Neumann machine is the generalization of any computing machine. Right? It all fits into this. Right? And so we can look at this kind of architecture, take this part, twist it around, and place it here, and you had your von Neumann machine. Right? It's so simple. Cool. So the stored program idea, just let's revisit this one more time, which is part of your compilation process. Okay? So we start with some program which is in text. Okay? You have your hello.c, and it's stored as data. So you have include space standard I/O, which is just stored as particular bytes. Okay? We take those bytes and we compile them into machine code, which is still, characters. Into assembly code, which is still characters. And then that gets translated pretty directly into machine code. So instead of, push L being 5 characters, we say that's just machine code number 55. Okay? And machine code 55 corresponds to some function on the calculator. The calculator doesn't have push that's exposed to you. Well, actually, it kind of does. It has the memory plus button. Okay? So it's a way to move data. So you're taking it from one type of data, which is just bytes representing characters, to another set of characters, which which is assembly code. Then you translate it into machine code, which is a series of instructions that your processor can actually do. Right? And then you have binary, which is just you take this and then you move it into a single string, and then your processor just kind of reads off things at a time and does a series of operations. Like, it's almost disappointing how not magical this is. Right? But this all comes from von Neumann, except he started with this, basically. And then over time, we added different levels of abstraction, because from this is hard to work with, so let's just have some characters. And then this is still hard to work with, so let's develop compilation, and the rest is history. Okay, so backing up again, we had the von Neumann machine, and then a lot of advances were in how to build better hardware. Right? So we started with vacuum tubes, which were kind of sitting here up top, and you had a bunch of wires and resistors sitting in these lattices below. So this is like IBM 700, first commercially available computer. Okay. Right? How many tubes do we have? 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. So that's a byte. Right? Obviously, this takes a lot of space. And so a huge advance was developing a transistor, which does the same thing as a vacuum tube, just in a much smaller format with a lot less electricity. Okay? And then once we had transistors, IBM developed IBM 7094, which was sort of the beginning of computer architecture. They were like, okay, we need to have these different things inside the computer to do certain things. But instead of building a monolith with all the stuff is just connected together, let's actually separate these out so they're sort of interchangeable. We can add them, we can move them, we can design them separately. And so they came up with sort of a first architecture. Right? So you have your CPU, you have your memory, And then you have this thing called the multiplexer, which is sort of like a network that connects different things. Okay? It connects to different data channels, and those data channels can be connected to different things like card readers, printers, disk or drum, which was ways of storing data, et cetera, et cetera. Okay? So now we're designing not just kind of faster way of doing computation, but also paying attention to how data flows by having an architecture. All right, so that kind of progressed for a while, and then eventually there were just sort of some limits into how these types of computers could scale, and so IBM bet the company on System 360, where they designed a new computer, a new family of computers from scratch. Okay? This is kind of the beginning of mainframes. All right, there's a great book called The Mythical Man Month by one of the key designers of this, and it's a really interesting book in kind of early software development or early system development. All right, one of the ideas is that adding more manpower late in the software project makes it later, which was contrary to kind of how production was made. Always adding more workers to a factory made things go faster, but the same thing turns out is not true for software or hardware, right? So that's kind of a big lesson. The other big lesson from that is that if you want to build a system, you basically have to build it twice. You build the first one, it doesn't work, and then you take lessons and you build the second one. So you might as well build this into your process. Okay? So this is the idea of refactoring, which we still have in test-driven development today. Right? As part of that, we're able to build circuits or print circuits. So instead of kind of laying out elements of circuitry and connecting them or soldering them together, now you could print these things onto boards, which became part of these types of machines. Okay, so after mainframes, the next advance was miniaturization of computers with DEC PDP-8. And the awesome thing is that this thing could actually sit on your desk, right? So you could bring it into an office much more easily than trying to buy a mainframe from IBM. One of the advances there was that it was one of the first uses of a system bus. Okay, we have different components connected all to each other over a bus, which was fast, simple, efficient, allowed this thing to become much, much smaller than mainframes of the past. Okay, so now all the computing things were actually in one box as opposed to spread around the room. Cool. So from there, we moved into microprocessors and semiconductor memory. Before, memory was, we'll talk about it later, but there were all kinds of ways of storing data which were just awful. But eventually, people figured out how to build semiconductors, and then also build microprocessors. So instead of having ALU here and your control unit here on a board, and then maybe a floating point unit, which was an add-on, soldered on later on, now everything moved into a single chip. Okay. So the first one of this was something called 4040, I think, or 4004, which was the first microprocessor, but it wasn't general purpose. And the first general purpose, I think, was the 8080 made by Intel, which looked like this. And it was the last chip designed by hand, purely by hand. Right? So there's literally someone that knew every single circuit in it, and it was laid out by hand. And then, people stopped doing that because it just became too hard. But this thing was used in this computer, whose name is, I forget. Do I have it? Yikes. Did I write it down? Hope I did. No, I didn't. Okay. I'll look it up and tell you guys if I remember, but you can see this computer in the Computer Museum, which is pretty cool. So it was using the 8080 chip. And so here you have your two slots for your floppy drives, the computer, and then you have a terminal, right, which has a display and a keyboard that were integrated together. So now this thing became much, much, much cheaper, and you could actually start putting this inside offices, kind of, if you were doing some sort of calculations. But it was still for people doing calculations. The next set of advances was the personal computer, with the idea of having a computer in every office, not just for doing calculations, but for kind of general business processes, right? The first sort of desktop, even though this thing sits under a desk, was the Xerox Alto, which developed the mouse and Windows-like interface, okay? At the time where Xerox was doing that, Apple and IBM personal computers still look like this. No mouse, no Windows. Okay? But these things were a lot cheaper, so people started using them, and then you had Windows 1 in 80-something. 1.1 was in 89, so I don't know. And then Apple had its own interface. But if you look at like the early screenshots of that stuff, they all have like some sort of file explorer. They all have a clock because having a clock with hands was apparently the thing everyone wanted, right? And they have some game usually, right? And all Apple and Windows just basically stole stuff from Xerox. Yeah, so then we have personal computers, and that's when you guys get born, so you know the rest. So, but anyway, that's kind of the brief history. So let's look at this in a little more detail. So we have a motherboard, and we have sort of a general architecture of a computer, right? And you can kind of compare the two and see that things match. So we have a CPU, which would sit here in this socket. You have your chipset, which is basically the I/O bridge that connects everything together. You have your main memory, which sits here in your DIMM slots, okay? Then you have an I/O bus, which kind of goes all over the place, but it connects you to a USB controller, okay? So you have your USB slots, I don't know, probably these guys, okay? You have your graphics adapter, which would be in one of your PCI Express slots, okay? You have your disk controller, which, I don't know, maybe it's this thing, maybe not, I don't know, but it connects to your SATA sockets, right? So, like, you can look at a motherboard and basically see this, right? Which is a von Neumann architecture. Same thing, right? Cool. So if you're executing a program, right, you can ask yourself again, what is the data flow in this? Which is very similar to the exercise we did earlier. We have some program that's, well, where does the program sit? Your disk, initially, right? It sits on your file system. So the first thing you got to do is you got to load it into memory. How do you load it into memory? Well, you got to go through the processor. That's not true. You do have things like direct memory access, okay? So the processor basically says, hey, disk, transfer this stuff to memory, and there's a direct line from here to there. Okay, so obviously we can speed this up, right, with better architectural design. Okay, so now your program sits in memory. Can the processor execute it? Well, not quite, because instructions need to actually move from memory into the chip, into the caches, right? So the chip actually works on memory that's stored within it on caches, right? It does stuff. There's output that goes either to, your screen or your or input from your keyboard, etc. But it's basically the same process with some improvements. Okay, so let's look at the execution of your hello.world. So the first thing that happens is that someone will type in hello, or you will type in hello. This goes to a USB controller. Through I/O, goes to your processor, which then executes some program for accepting input and stores it in memory. Okay, stores the words in memory. Then hands it off to the operating system, which will read this stuff and say, okay, we want to run the hello program. Great. So now the operating system will look on disk, find the hello program, transfer it into main memory, okay? And then once it's in main memory, it can transfer to the CPU. The CPU will run it and then send data to the graphics adapter to display hello world. Okay? So the process takes some number of steps, but they're all, if you really think about what each functional unit does, pretty predictable, right? You can kind of break all the things that have to happen into discrete steps. Once you have discrete steps, you can have hardware that does these discrete steps. The hardware doesn't have to be general purpose, but together, by being able to follow this process, not general purpose hardware such as memory starts performing a general purpose task. And that's the beauty of it. Okay. So let's talk a little bit about memories. And so you have your main memory, which stores data, but for the processor to execute it, it can use cache, but it really doesn't use the cache other than to move data into the register file. Okay, and registers are distinct storage points that you can address to do computation. Okay, so if you're saying, hey, ALU, add this number and that number, that this and that are the first register and the second register, and then put result in the third register or overwrite the first register. Those are kind of the things you can do, right? The ALU is pretty dumb, but if you tell it to operate on two things and put the output somewhere, it doesn't even really understand where the cache is. It's connected directly to the register file. Then the control unit can move data from the register file into cache memory, eventually into other memory. Okay, why do that? Well, it has to do with speed, right? So you can think of your memory hierarchy as different areas to store data or different areas to store stuff, right? So in your dorm room, you're going to have a fridge with stuff that you need, right? But the rest of the stuff that you need is probably at Costco. You just can't put all of Costco into your fridge. Why not? Well, because it would take too long for you to walk around through a fridge this size to find whatever you wanted, right? There's just some space thing. Well, why have a fridge at all? Well, because anytime you want a can of soda, you're not going to go to Costco and walk the aisles to pick up one can. All right, so it makes sense to have some sort of items closer to you and some sort of items further away. Right? And so the same thing happens on your chip. Okay? The thing that's closest to the CPU are the register. Maybe 32 registers, just like you can put, I don't know, 32 items in your fridge here. Okay? Then you have your level 1 cache, which stores more stuff, but it's a little bit further away. So you gotta, go further down the, away from your ALU to fetch the data. You have your level 2 cache, level 3 cache, which are just bigger things. Then you have your main memory, and then you have your disk, and then maybe you have like cloud storage. Right? It all does the same thing. There's some different granularity, but it's just a factor of speed and versus size. All right. So this memory hierarchy is used by the operating system to create the illusion that each program has access to all of the memory, right? All of the memory here, the main memory, but it all has the performance of the register file. So it's all super fast. It's like you basically think you have access to all of Costco, and then anytime you reach in the fridge, you get whatever it is that you wanted instantaneously, right? The operating system will provide this illusion. Doesn't always work, but it works a lot of the time, right? It's like having like a super assistant that just spends their time trying to guess what you want. Okay, they're going to want a soda. They're coming back from class. They run to Costco, get the soda, put it in your fridge. You get there, soda, right? That's what the operating system does. All right. It does other stuff too. Like, for example, when you need to access hardware, well, the CPU doesn't know anything about hardware, but it does know how to write data to memory. So if we take hardware as sort of the process of reading and writing data from your keyboard, well, we can map that into memory, and then whatever data people type into keyboard, that appears in your memory, and now your CPU can grab it from memory. Okay? Yeah, and that's basically everything. So, yeah, I'll finish later. Let me just pause my recording if you don't mind. All right, and